Welcome to the video podcast series here at Ontario High School. We're looking at gas stoichiometry, and specifically we're going to look at the standard molar volume of a gas and its usefulness in stoichiometric calculations. So appreciate you being here, and let's go on. I want to look first at defining standard temperature and pressure. And standard temperature and pressure are the conditions under which the standard molar volume of gas is 22.4 liters. And what that means is 1 mole of any gas will occupy 22.4 liters at STP. At STP, our pressure is equal to 1 atmosphere. If we want to put that in different units, we can, 760 millimeters of mercury or 101.325 kilopascals. Those are the two most common other units you'll be using. I want you to remember as well that the millimeter of mercury is often referred to as a torr, T-O-R-R, but their quantitative value is the same. The temperature at standard temperature and pressure is always expressed in Kelvin. It's 273 Kelvin. Since we won't always be at STP, in fact most of the time we are not at STP, we'll be using the ideal gas law at times. The ideal gas law involves a value that's referred to as R. It's the universal gas constant, and you should write these down. R depends, the value depends upon what the pressure units offered in the problem are. So when pressure is in atmospheres, the value of R is 0.082 liters times atmospheres over a mole times a Kelvin. When the pressure is in millimeters of mercury or torr, R is going to be 62.4 liters times millimeter of mercury per mole times a Kelvin. We have one more that we'll express on the next slide. When the pressure is expressed in kilopascals, then the value of R is 8.31 liters times a kilopascal per mole times a Kelvin. Well, several keys that are important to solving problems of stoichiometry type that involve gases. And in all our stoichiometry problems so far, we have talked about how we can only compare chemical quantities using the mole. So it's very important with gas stoichiometry that you get to the mole. So get to the mole. If at STP, use the conversion factor that relates 1 mole to 22.4 liters, which is the standard molar volume of a gas. If you're not at STP, then you must use the ideal gas law, which is pressure times volume is equal to the number of moles, N, times the value for R, the universal gas constant, times the temperature in Kelvin. Continuing with our keys to solving problems that involve gases in stoichiometry, once the number of moles of the gas are found, we fill in the BCA table and solve for the desired value. Let's look at a sample problem. On this podcast, we're going to do a sample problem that involves a gas that's at STP. The next podcast will deal with a gas that is not at STP. So this one is the simplest form of gas stoichiometry problem when we're dealing with what we would call a mixed problem, where we have a gaseous reactant as well as a non-gaseous reactant and product involved. So we have 14 liters of chlorine gas at STP is reacted with 12 grams of solid sodium metal to form solid sodium chloride, NaCl. How many grams of sodium chloride would be formed? We're going to find our theoretical yield, and we want to know how much of our excess reactant remains. And it's really critical here that as you look at this problem, whenever you're given a quantity for more than one reactant, this is a limiting reactant problem, and you need to pursue it as such. So that's what we're going to do first. Our balanced equation is 2Na solid plus Cl2 gas yields to NaCl solid. This is a wonderful synthesis reaction as a reminder to our reaction types. And if you were to just be given the reactants here, sodium and chlorine, and asked to write the product, you would just form the binary compound of those two elements. Since this is a limiting reactant problem, we need to find the moles of each reactant before we can compare them and see which is going to run out first. So for our sodium, we're going to multiply our 12 grams of sodium by the conversion factor that relates 1 mole of sodium, which would go on top, to the mass of sodium in 1 mole of sodium, which is 23 grams. So when we do that, we get that we have 0.522 moles of sodium. For our chlorine, because it's a gas at STP, we're in really a nice situation here, because we know that 1 mole of chlorine will occupy 22.4 liters at STP. That's the standard molar volume of a gas. So we take our 14 liters of chlorine times the conversion factor that relates 1 mole of chlorine on top to 22.4 liters of chlorine on the bottom. When we work this out, our liters of chlorine cancel, and we're left with 0.625 moles of chlorine. Once we've found the initial number of moles of each of our reactants, we can fill out the before line in our BCA table. So we put our 0.522 moles of sodium there and our 0.625 moles of chlorine. Notice I don't have to write the unit moles in the BCA table because nothing goes there except 4 moles. Our change line and our after line we're going to leave empty until we find what our limiting reactant is. So by my convention, I always start with the leftward or the first written reactant, and I'm going to find the number of moles of chlorine that I need to completely react my moles of sodium. And I'll do that using the mole ratio. So 0.522 moles of sodium times 1 mole of chlorine over 2 moles of sodium. That mole ratio is using the coefficients in the balanced equation, and the only time you will ever use those coefficients in the balanced equation is when you use a mole ratio to go from moles of one reactant or product to moles of another reactant or product. When we do this, what we find is that we need 0.261 moles of chlorine. Well, we settle which is our limiting reactant by looking at the moles of chlorine that are required. We need 0.261 moles of chlorine. When we look at the before line in our BCA table, we have 0.625 moles of chlorine. So we have much more chlorine than we need, meaning that chlorine is in excess and sodium is a limiting reactant. Since we know what the limiting reactant is, that's what we're going to use to find how much things change by. We're going to use up all our sodium. So that's going to be minus 0.522 moles. And we know from our calculation to find out how much of the chlorine we needed to react that much sodium that we're going to use 0.261 moles. So for the change we'll have minus 0.261. Then the great news is that sodium chloride shares the same coefficient as sodium. So if sodium changes by minus 0.522 moles, then sodium chloride would change by the same amount, only in the plus direction, the positive direction. So our change for the sodium chloride is plus 0.522 moles. After this reaction is done, we should have none of our sodium left, so we have 0 there. The amount of chlorine would be our starting amount, 0.625 moles, minus what we used here, 0.261 moles, and that gives us 0.364 moles of chlorine left over. The amount of sodium chloride that formed is 0.522 moles. Once we have the moles of the chlorine that are left over and the moles of sodium chloride that were formed, and again we just look at the after line in our BCA table, we can go ahead and find then what the problem asked for, which was the mass of the sodium chloride that formed. So we take our 0.522 moles of sodium chloride and we multiply it by the mass of sodium chloride, 58.453 grams, that consists in 1 mole of sodium chloride. So when we do that, we find that we form 30.5 grams of sodium chloride. It's very difficult to find the mass of gases logistically, so we tend to use the volume of gases that form rather than masses. And this is real easy to go with here. We have 0.364 moles of chlorine, and we are going to multiply that, because we are still at STP, by the standard molar volume of a gas, which is 22.4 liters of chlorine for every 1 mole of chlorine. When we do that, we'll find that we started this reaction with 14 liters of chlorine, and we end this reaction with 8.15 liters of chlorine left over. So there you have it. That is how you would use the standard molar volume of a gas, 22.4 liters of gas per 1 mole at STP, in a stoichiometry problem that involves gases at STP. I think I said that about 12 times, and the hope is that will stick in your memory so that you'll be successful doing these problems. Well, this is the end of the gas stoichiometry video podcast, part 1. There are several more parts to come. Stay tuned for those. In the next podcast, we'll deal with how to use the ideal gas law to find the moles of gas when you're not at STP, which is a very important skill to have. So I want to leave you with a quote by great British statesman Edward F. Halifax. "Hope is generally a wrong guide, though it is very good company by the way." What a wonderful quote. I wish you well.